Okay, thank you. So this talk will be mostly about the database performance, but so I'm using Django as a tool, but it still applies to any other framework, and you can do it with the raw SQL as well. I'm just using Django as a tool to interact with the database. So if you are not using Django, then it's okay. It's still applicable for you as well. So first about me, I used to work for a lot of years kind of on a bleeding edge of performance and tuning databases. So we went through like the old style spinning disks, SCSI disks for enterprise servers, and then different set of RAID disks like network attached storages and so on. And then finally we came to SSDs, and then I thought, okay, so we are done, no more performance tuning. So now I'm working mostly with RDS and AWS, and guess what? I'm still doing performance tuning. And so what I find out is that mostly it's because people misunderstand the databases. So I will try to explain, like for a developer, how the database thinks. And so this is kind of slide. So the correct answer for every problem is that, well, it depends on your situation, your specific hardware, and so on. So I will try to do like generic advice that probably is fine for 90–95% of the time. If you find those 5%, then don't blame me. I know about them myself, but so I will try to give you a specific advice. So a bit of theory first. So how the database stores the data. So it's stored on the disk. It's stored inside the blocks. So each block contains multiple records. And then it's all stored sequentially on the disk. And so whenever the database wants to find something, so it goes, in this case, from the left to the right. And it scans through all the data until it finds what you ask for. So in Python, it would be something like a list of records stored in a list. So then obviously, so this is not fast. To speed it up, databases typically use indexes. One of the most popular are the B-tree indexes, which stand for balanced trees, not the binary trees. And so those are trees. How does the lookup work? So let's say you want to look up the key with value 18, so it will find the largest element that is less than the element you are looking for. So here it finds the element 15. Then it jumps to the branch. It does the scan on that kind of level as well. It finds that the 17 is the value that is the largest value that is still less than 18. And then from there, it knows that it has to go inside this like leaf blocks. And inside the leaf block, it finds that, okay, we have the 18 there, and it contains some data. So typically for Postgres, this data is the physical address of the record on the disk. There are some other databases like MySQL, where for the primary index, it will contain the whole raw data. Or for the secondary index, it will contain the value of the primary key. And then with that primary key, it goes to the primary key index and then goes through the index and finds the data there inside the index, inside the primary key index. And yeah, so once it gets this physical row ID, it goes to the database block. And then it does some quick search inside the block. So because this physical address is like on the block level, not on the physical byte level. But in practice, it looks like more like this, especially in Postgres, where the data is appended and reshuffled during the vacuum. So it's a complete randomness. And like these pointers are all across the data. And just to give you an idea, if we would try to model this in Python, we would have a dictionary for an index. So this is not entirely true because dictionaries in Python are hash maps, while the indexes are trees. So they have a different set of properties, but for the purpose of this talk, stay with me. So what this dictionary contains is the key and then mapping to several indexes inside this table data. And then, so how does the database decide how to look for the data? So there are a lot of, so it calculates the costs of each operation and decides which is the cheapest one. And there are multiple parameters inside the database. The most important ones are the sequential page cost. It means how much does it cost to read the next page after the kind of current position on the disk. So it goes back to the old spinning disks. So the value there is 1. And then for the random page cost, since we have to kind of move the reader head and spin the cylinders and so on, so the cost is of course higher, so it's 4. And this 4, the Postgres documentation says that actually it's closer to 40, but we assume that 90% of the lookups will go through the cache, therefore we say that random page cost is 4. And they also recommend that it should be 1.1 for SSDs, so because for SSDs the random access is pretty fast. Now the question for you is, so typically you use some database in a cloud provider, let's say AWS. How do you think, what is the random page cost there? It's still 4. The databases in AWS work as if they worked on the spinning disks. So they assume that doing a random access will be extremely slow, when in fact it's not. And then there are some other costs that are associated with choosing indexes, but those are, if you compare to like page costs, those are like 0.0 something, so you can most of the time you can ignore them, so those are not important. So let's think like a database. So we want to find all keys from 17 to 21. So, and database, things like that. So I know how many blocks I have for this table, and I have to scan through all of them to find those keys. So how much will it cost? So reading one block costs 1, 2 will 2, and so it goes through all the blocks. So it knows that the total cost in this example will be 8, and it will find all the keys by doing this. So now the other choice is to use an index. So just a reminder, this is the data pattern that I'm playing with. So since it's going to use an index, it already, even ignoring the index cost itself, it knows that, oh, I will have to read a random block in the table. So it costs 4 for key 17. Then I will have to read another block. It will cost me 4 again. Then another block, 4 again. And so we already paid much higher cost than just scanning the table. And out of this, it should be kind of obvious that if we need to access a single record from the table, then it's much faster to do this through the index and to pay kind of this high random access cost. Then accessing all table records, it's probably cheaper just to scan the whole table. And then there's something in between. And most experts will tell you that it's single-digit numbers. So if you need to access, let's say, up to 3% of the table, then it's faster to go do it through the index. And this basically boils down to these cost values of sequential access is 1 and random access is 4. So those are the numbers that play the most significant role. And on top of that, databases are also often bad at estimating what percentage of rows it will return. So I will show some examples of that. So even if all goes well, database might have another opinion about your data and screw it up. And also for the indexes, so typically database prefers to have like one index with all of columns instead of several small indexes. It's because for each index, there's some associated cost to go through the index itself. And to go through an index itself, it's also the random access cost. So while index is smaller, it's still like very, very costly. And the generic advice is to index high cardinality columns, which, so it might be the transaction ID, email, phone, and so on. And to do not put index on the low cardinality columns like Booleans, or let's say for transaction processing systems like currency, because typically most systems process like what? Most of the transactions will be in 2, 3 most popular currencies, and the rest will be somewhere behind that. And if you really have to do that, then look into the partial indexes which Postgres provides. So that being said, now it's time for practice. So I have a simple model in Django. So I have a member, which is kind of person, and the most important, the member has a name. And then there are some documents, and the person can have multiple documents, and documents have some status, so one of the 3 values, and then some data, which is JSON. So this is the kind of setup to demonstrate some of those things. And then I generated some data, so I started with 10 records, but then the database didn't perform as I wanted it to, so I generated some more records. So, and this is one of the lessons you have to learn, that if you want to do database tuning, you have to do that on a realistic data. Whatever works in the developer environment won't work in production. So if you can try it out in production environment, it's perfect. If not, try to find something that is close to that. And for the Django, how to see what the database is planning to do, there's this, for query sets, there's this .explain function which returns, like, most of the databases have some kind of plan where it tells like how it's going to execute the query. You can do like the same also in the raw SQL by typing explain and then the SQL statement you have. But I'm using Django here. So I have a query that finds a member with a specific name, Karen Long, and I say explain. So, and typically how I read those are bottom up. So I start from the bottom. I see that, OK, it will use an index on the name, which is really fine. And then it's using this index scan. So perfect. This is how it should be. Now, however, the user input comes in different forms. So I want, oh, sorry, not yet. So the other very important flag is this analyze equals true. So what it does, instead of just the database telling you how it thinks it will execute it, this is actually force the database to execute the query and then report timings back to you. So this is kind of reality check for the database. And what you get the planning time, and most importantly, the execution time of query. And you also get some actual time for each of the operation and actual rows returned. So oftentimes you have that on the estimation, it says that it will return 200 rows, and in the actual reality, it returns just a single row. So this is where the database statistics screw you. So yeah, and this is sometimes we get this kind of input that is not like, let's say the cases are not correct. So if we try to do like a case insensitive search, so in this case, it's instead of using the index, so we know that we had an index on the name, it's actually going through the whole table and scanning the whole table. So it's going to be slower most of the time. And you can see that by this sequential scan on the table instead of index scan. And to explain this to like developers, let's say you have this nice index on the names. And for the dictionary, there is no operation where you can look up the dictionary key by some mixed case representation of the same key. So it just doesn't work. So that's why database is not able to use the index that is created like this, but we want to get like case insensitive lookup out of it. So in a nutshell, if you see sequential scan on some table, it means the database is really scanning the table, and whatever is written there on the filter, it's the index the database is trying to find. And most of the time, it's also a hint that you should create index like that. And when it says index scan using, then it's really using your index, and then the index condition just kind of shows you that whatever was used there. A bit reminder, so we had document status with 3 values, and specifically for the value unknown, I made it so that in the generated data, it represents around 5% of the whole data. So the property of the index is that it kind of works for the positive expression, so for equality, and because it's the tree structure, it also works for less than or greater than. So here, when I'm looking for specific value of the document status unknown, it does use the index, and everything is fine. However, keep in mind we had just the 3 values. So here I'm asking for the exactly same set of rows. I'm just formulating my desire differently. I'm saying, please do return anything that does not include those 2 different other statuses. So if we go back to statuses, the only value left there is unknown. So we filter out valid and valid, so it leaves unknown. And although to us it is the same, it's not the same for the database. So database doesn't work on like inequality. So whenever it sees inequality, it does the full table scan. So one of the ways I have fixed it before, so first in the Python, so again, we have dictionary, so we have these 3 keys, and we list of rows that it matches, and we do not have expression on a dictionary that says, oh, return any key except that is not one of those. So we do not have that. So therefore, it doesn't work also in the database. And so the way to fix it is to kind of calculate the positive expression in the user code. So I have a set of all possible values. I subtract the values that I do not want to see, and I get the values which I actually want to see. And then I write it in a positive way, and the database is able to use the index as it should. So now let's create some missing indexes for the queries. So we want to fix this kind of query that does like case-insensitive lookup. So what and here the database tells us that it's looking for upper on the name. So that's the condition it looks for. So for that, we have to create an index. So it's a Django syntax, but it's the same for, you can easily translate that to SQL. So we are creating index that is upper on the name. And so what we essentially are doing is we are creating an index with all uppercase keys. And then, of course, this lookup will succeed. And indeed it does. So it uses this right index condition. It finds the newly created index, and it's great. Now, so all this talk started kind of attempt to do the live search queries, which is like user types some characters and system returns all the things that kind of match the query that has been entered. So here I want to show members which somewhere in the name contain the 3 letters. So again, if you look at the query, it's looking for the filter condition on the upper name. So that's the index we just created. But still, the condition doesn't work. And just for so this is Postgres specific. Like plain SQL, it's trying to do the like operator on this filter condition. And the thing is, B-tree indexes do not support that. So therefore, to fix that, again, Pythonic example. So we have these kind of keys, and we can't look up in the dictionary by just having a part of the key. So there's no such operation, and therefore we need to build some kind of a different index. And Postgres has this GIN, so generalized inverted indexes. I won't go into details, but just to explain you how those work, again in the Python. So what it does, it splits the keys in a triplets. So all combinations of 3 letters that are inside of a key. So, and we do here that on the upper string, so because we want to have case insensitive. And then the index is built built for all these 3-letter triplets, and it maps to the rows where this name can be found. And then whenever we do query, then it does again, splits the input into triplets, looks up each triplet individually, combines the resulting rows, and returns that to us. How to do it in Django? There's a bit of a magic. You have to add you have to add the package with Postgres, so it's for let's say, just ignore it's for some Postgres things. And then once you have that, you can create a gin index with operator class, upper name, and so on. And then you specify this trigram, which is, you don't have to understand all of it. It's just something you have to do. Once you create the index, you also have to do the migration. And typically, I try to do that on the first migration on the project, where I simply add the trigram extension. So that's the thing. And the funny thing is, if you forget to add this to your installed application, you will get really, really strange errors when migrating running migrations. So once I did this, and somehow it still doesn't work. Any ideas why? Yes? Good idea, but no. No, I created the gin index for. I get your idea, but no. This is a trick question. So the fix is to analyze the table. So sometimes if you create indexes, the database doesn't have the statistics. So whenever you do this kind of tuning, after every change you do to the database, do an analyze, and there are other things like you flush the buffers and so on. So just to start from a clean slate, because this leads to a lot of, you can go into half an hour exploring one area just because you forgot to do the analyze. So now the fix fixed that, and now it's using the index, and it's all good. So we are doing, so I contains on the gin index that is on the upper of name. But then let's say we want to do case-sensitive live search. Again, so index doesn't work. And why? Because if you look at the filter condition, it's basically it wants a trigram index simply on the name, not on the upper of name. So this is like often source of confusion. And then again, explaining in Python, so we have index which is on the uppercase triplets, but we are trying to look up like something on a case-insensitive way. And let's do JSON. So Postgres has this nice JSON-B column, which basically, for me, removes need for any like document database. So I want to do the live search on the JSON field as well. So Django has this nice syntax where basically I have inside the data field, there's JSON element document number, and it should contain some kind of characters. So when I try to run it, it says that, oh, it's looking for the upper on this document number, and because it's using this, I don't know how to say that in English, basically this like operator, then I know, okay, so I need to have a gin index. Let's do that. And to be honest, I did this by trial and error. So you write something in Python, you try to run it, it says, oh no, something doesn't work in Postgres, so I found out that you need to do the cast thing, so okay. And the Python itself doesn't tell you anything about this. So I did the index. It still doesn't work. Any ideas? No. That's a trick question. So yeah, I did analyze the table. So what's interesting here is I hope I can formulate the bug to Django at some point in time. So we created index, and if you look closely there on the index, look closely here. So and those greater than matter, because one of them tells me, please return the string, and the second one tells me, return whatever JSON object there is, and it's not the same. For database, it's not the same. So at this point, I was like, I already had some pain getting to work it through Django. I just said, let's do the SQL stuff. And honestly, it's much, much easier to do it this way. So I did this correct operator with 2 greater than, and ta-da, it works. And now it's the time to put it all together. So in the project, we tried to do this kind of search across multiple tables in Postgres. And the condition was basically, so return, let's say, so this is a simplified example just with 2 tables. In practice, it's something like 8 tables. But let's return all members which have something in the name or something in the attached document. And guess what? So we have indexes for all of these individual columns. And now is the Postgres. So if we start going up from the bottom, so it does sequential scan on members. Why? We do have an index for the condition. Then it does it has the word hash. So basically and then it does the second scan on the explain document. So basically what it does, it creates a huge multiplication or product of those 2 tables. And then on the top, then it decides to do the filter. And of course, there are no indexes for that. And this is the polite word. Once I understood that, I was pretty angry because I come from the mostly Oracle background, and Oracle isn't this stupid. Oh, I said it. In more expensive ways. OK, so how to fix this? So this is where you have to kind of be creative. So what I'm doing here is I'm collecting all IDs of the members. So first I get IDs of the members table where the name contains something. And then I do this, it's the union. So in SQL, it's like select something, that union, and another select. So basically, I'm joining the several, in this case, 2 data sets inside the database. And then I also join members which have document with data and so on. So it's basically, I'm doing the same thing. I'm just expressing it differently. And guess what? It kind of works. So this is scary, but let's break it down. So first, it is at least like 5 times faster. It actually uses the index. This is so on the document number. And I want you to pay close attention. So it estimates that it will have 85 rows. In reality, it had 0. In a similar way, it did the same on the name index. Again, it estimates that it will get 85 rows. In reality, it gets, what, 22. So this is where statistics mess up the execution plan. And the main point is that it gets faster. Then we did some kind of simplifications. So then the query becomes less scary. So instead of doing the second union, so if we go back here, you see the second union pulls in members containing documents. But here we just say, just look at the documents and return what is member ID out of those documents. So it simplifies, and so it gets even better. And so that's it for my talk. So just to bring to you why it's important. So there's this research paper that looked at the open source databases and to find out how they are broken. So it looked at Ruby on Rails. But I mean, this is like very similar to what we have in Django. And the number one reason for slow performance was missing database indexes. So that's why this talk is important. And to be totally fair, this scored something like 17 or 16. And the second worst thing was n+1 queries, which scored just a single point less. But missing indexes win. Yeah, so that's it. So this is kind of a cheat sheet. Whenever in Django, you do like direct comparison, you create a simple index. If you want to do like case-insensitive match, then you create index on upper, and then there's I-contained. So I have seen cases where people create this gin index, but they create that simply on the field and then do the I-contains, which of course tries to look up the different kind of index. And so this is it. Thank you. So there's the GitHub repo. So it has the scripts I played with to reproduce the behavior. So do you have any questions?
Okay. Yeah, thank you for this presentation. Back to the case where you used the negation query and replaced it with positive comparison. In Postgres, there are native enums. Do they work natively with negation, since enum has few values only? Does it work out of the box? Do you know?
Yeah, so I'm not sure about that case, so it would have to be checked. The thing is, if you use Django for migration, Django doesn't use these kind of enums, so the Postgres database is not aware of the potential values. So I guess that's the reason the Postgres is not available to calculate those. But yeah, so that's something you could look up. For me personally, I do not like to enforce those kind of things inside the database, because whenever we have to change its database migration, it's kind of painful. So I prefer to keep those in the application code, which is like not a typical advice, something like a DBA would give you, but that's my preference.
I see. Thank you.
Thank you for the presentation. It was really nice. I was curious, so at the end you showed a couple of examples where the raw output of the explain analyze starts getting a little bit hard to read. So I was curious if you use any tools to make it more readable. I've used the explain deeps in the past. So yeah.
Yes. So I know there are like graphical tools to show that, and yeah, there are different types of output you could ask for, JSON output, for example. But for me, its textual format is easier to read. So the longest explain plan I had was more than 1,000 lines. But yeah, I don't think like graphical representation can help you with that. So if you are new to that, definitely try out the graphical, because they might show some more hints on top of those. So kind of explain what the actual row of that means. To me, I'm kind of used to this kind of output, so for me it's easier to like, it's kind of more condensed and it doesn't show a lot of additional information, but that's enough for me so I can digest it.
I would try an LLM.
Yeah.
It might help.
Sure.